to talk about model calibration. I think we've been here before. And we're going to talk in particular about what model calibration can and can't achieve. We're going to start off with the situation statement that we ask, well, if I am going to calibrate a model, if I am going to seek this unique thing called a calibrated model and then go and make important predictions with it, what am I actually seeking and what are the conditions under which I should seek it? So we're going to first set the context for what calibration can and can't do. And then we're going to say, this is how we do it, just using the maths we revisited last webinar. And then we're going to finish off with a very powerful situation statement about just what calibration can and can't achieve. So remember from last time, we said, here we are, we want to calibrate a model. So we've got a model, and remember I said I'm going to characterize the action of that model on its parameters using this matrix Z. So I'm going to assume linearity. Now, all the equations that we're going to derive are based on a linearity assumption. When we use these equations in the real world, we're not bound by that linearity assumption. We just apply them iteratively so we can get over model nonlinearity. Anyway, we reckon we know the processes that are operative in the real world, and for the purposes of inversion theory, we encapsulate them in a matrix Z. That model has parameters, many but not all will represent system properties. That model produces outputs, and we have field measured counterparts to those outputs. Now, those measurements are contaminated by error, and I'm going to characterize that using this vector epsilon. Now, we know, as we talked about last time, that things that are responsible for model to measurement misfit, which is what that epsilon is representing, it's more than just measurement error. It's model structural defects, model conceptual defects. But I'm going to put those little horrors to one side. There are ways to accommodate that, but we're not going to talk about that because it does get a little bit ugly. At the moment, we're going to assume for convenience that it's measurement error. And what that allows us to do is to make some simplistic assumptions about the stochastic distribution of epsilon. So there's the equation. What I observe in the field is the action of the model on my parameters plus measurement noise. So as a modeler, that's the equation of my life. So what do I know going into this? Well, I reckon I know the processes that are operative in the study area. I've done site characterization. I don't know what's under the ground. I don't know the hydraulic properties of the subsurface, but I do know, I know what's not there. So I know the preferred values, the expected values of those hydraulic properties just based on the geology that exists. And I know the propensity of rocks to depart from those preferred values. And that's encapsulated in this CK matrix, this covariance matrix of hydraulic properties. That's encapsulated in that covariance matrix of hydraulic properties. So, and we said last time that hydraulic properties will show spatial variability, which I encapsulate in that CK matrix. So I'm not going into this process empty-handed. There's stuff that I know. And of course, I know the field measurements. And epsilon, measurement noise, I don't know that. But as we were talking about a moment ago, I'm going to assume that its expected value is 0, and I'm going to assume that C epsilon, the covariance matrix of measurement noise, has only diagonal elements. So there's the equation of my life, and there is the situation statement. So here's my observations, of which I'm assuming there are n of them. Lots of parameters, because in every cell of our model domain, the hydraulic properties can be different. So I'm happy to assume lots of parameters. And because I'm assuming lots of parameters, this Z matrix here, I'm assuming that it's got more columns than rows. That is, that this data cannot inform all of these parameters. So I'm looking at reality right in the face here. The Earth is infinitely heterogeneous, and I'm prepared to accept that, and I'm prepared to use a K vector of model parameters that can be very large, meaning that my Z matrix here is going to have a lot more columns than it does rows. So that is a statement of my situation. Now, let's define this situation mathematically. Let's spend a few moments giving mathematical characterization to the land in which I'm walking when I want to calibrate a model. So here's my Z matrix. Now, because that matrix has more columns than rows, then some of those columns are going to be linear combinations of other columns. And in fact, that'll happen as many times as there are number of columns exceeding number of rows. So this is a multi-dimensional thing. So that Z matrix is column rank deficient. Now, we talked about column rank deficiency in the previous webinar, and that has consequences. Now, matrices which have more rows than columns can also be column rank deficient, and that has the same consequences. And those consequences are pretty important when we're talking about model calibration. So let's look at those consequences. So let's just ignore measurement noise, H equals ZK. Now, I'm going to introduce this concept called the null space, because it's this that characterizes our situation more than any other. A matrix has a null space if there is at least one non-zero vector, delta K, for which Z delta K equals 0. Now that may seem a little bit abstract, but it's really important. If a matrix is rank deficient, it'll have a null space. If a matrix is longer than it is deep, then the dimensionality of that null space will be at least equal to the number by which columns exceed rows. What are the consequences of Z having a null space? Well, let's add the blue equation to the yellow equation, and we get the green equation. And the green equation says that if I have found a K, a set of parameters that allow my model to match field data, then I can find another set of parameters that allow my model to match field data simply by adding on something from the null space. So null space equals non-uniqueness. The inverse problem is ill-posed, and this is the land in which we live whenever we're doing any kind of history matching, whether it be for uncertainty analysis or calibration. So let's just spend a couple of minutes now talking mathematics about what our situation is, so we can better understand it, and having understood it, we can better define what it is that we're trying to do when we calibrate. So continuing to ignore measurement noise. We need to find some vector K underscore such that H equals Z K underscore. That I'm going to call the solution to my inverse problem. Now, what I'm going to do if I'm going to describe that mathematically is I want to find a matrix Z negative, a generalized inverse of Z that allows me to calculate K underscore from H. So that's my job. And that Z negative, the mathematicians give it a superscript negative, is my generalized inverse. Let's substitute the yellow equation into the blue equation. Let's now pre-multiply both sides of that equation by Z. And let's now just simplify things a little bit. This green equation is the mathematical definition of a generalized inverse. Z equals Z, Z negative Z. Contrast that with the definition of the inverse of a square matrix that we talked about in the previous webinar. there's big differences. In the previous webinar, A is square. Its inverse, characterized by a -1 superscript, may or may not exist. If it exists, it's unique. This is non-unique, and Z doesn't have to be square. So that generalized inverse concept and its definition makes it very clear that we are living in a non-unique world. Yet, when we calibrate, we seek uniqueness. So we need to be very specific in what we seek. And it would be nice if we were to attain uniqueness in a way that benefits, well, modeling and decision-making. Well, it just so happens we can, but we got to be careful in how we do this. A little bit further on this abstract mathematical journey, there's the definition of the generalized inverse. Now, there is a special generalized inverse called the Moore-Penrose pseudo-inverse, characterized with a positive subscript instead of a negative superscript, sorry. So it is a generalized inverse, so it obeys the generalized inverse equation. It also obeys 3 other equations, mainly specifying symmetry relationships. Why am I telling you this? Well, the Moore-Penrose pseudo-inverse is unique. Okay, we have uniqueness, so what? The so what is that gives us the vector k underscore, which has minimum norm, which under certain circumstances is minimum error variance. So now I can start to bring the mathematics and calibration together in ways that are good for the decision-making process. By the way, preempting what's coming up, singular value decomposition gives us the Moore-Penrose inverse. So that defines our situation. We, when we seek to calibrate a model, are seeking uniqueness where uniqueness has no right to exist. The general term that mathematicians give to turning ill-posed problems into well-posed problems is regularization. But we want something more than that. We want to calibrate a model, and we want to do it in a way that's good for the decision-making process. Well, it just so happens that our desires and mathematics coincide here. We can attain uniqueness, which is what we want, if we specify that out of all the possible solutions to an ill-posed inverse problem, we want that which allows our model to make predictions which are somewhere near the center of the posterior probability distribution of those predictions. That is, minimum error variance predictions. That doesn't mean the error variance or the uncertainty of those predictions isn't very high. All it means is that I've minimized that predictive error variance by making the potential for error symmetrical with respect to the prediction. So here the mathematics and our desires coincide. It can be shown mathematically that uniqueness is attainable, and it's attainable in a way which allows me to make predictions of minimum error variance. That's my goal. And when I calibrate a model, I've got to be sure that I attain that goal. Now, there's 3 broad approaches to regularization: manual, subspace methods, and Tikhonov. Which do we use? Normally all 3. Tikhonov does the heavy lifting normally. We use a bit of manual. For example, when I use pilot points as a parameterization device, that's not cell-by-cell parameterization, but it's Tikhonov that, for reasons we'll talk about, we should depend on. However, we'll also talk about SVD because that gives us uncompromising numerical stability when we come to solve an inverse problem. It also gives us unique insights, as we'll see, into what we can and can't achieve when we calibrate a model. Firstly, manual regularization. So that's my situation statement there on the left. And if I'm going to manually regularize, I've got to manufacture this artificial situation. Same H, same epsilon, less parameters. And therefore, a X matrix rather than a Z matrix, working on a P matrix rather than a K matrix. And that X matrix has more rows than columns. So using some kind of parameter lumping, fixing, pushing parameters together, whatever it takes, I try to achieve this situation. Well, I can achieve this situation, but I just hope and pray that that problem is now well posed. So this now becomes my artificial situation for the sake of undertaking manual regularization. How do I solve for P? Well, I do that through minimizing an objective function. And that's defined in terms of residuals. A residual is the difference between an observation and a respective model output. So the ith residual is the difference between the ith observation and the ith model output. Q is a weight matrix, normally diagonal. So this objective function is the sum of weighted squared residuals, which you're mostly familiar with. The higher the objective function, the worse is model to measurement misfit. If I minimize that objective function, I obtain this equation for my estimated parameters. Okay, I've solved the inverse problem, but I hope and pray that that inverse exists. If it doesn't, I'm in numerical trouble. So here's my artificial situation. And I'm going to leave out the Q just to make the maths a little bit easier. Here's my estimated parameters. Let's substitute H into this side. And I end up with this second blue equation. Inverses cross out, and I end up with this third blue equation. Take P from both sides, and I've got an equation for parameter error. But don't forget, these are artificial parameters. Anyway, for the moment, I've got an equation for parameter error. Notice that it depends only on measurement noise. That's a bit unsettling. We'll get back to that. But it also means that I can't calculate my parameter error because I don't know the noise. However, I can calculate my propensity for measurement error. So how do I do that? Here's my equation again. And remember back from webinar 1, this beautiful equation, which we said we'd revisit again and again for propagation of covariance. If y equals ax, the covariance matrix of y equals A times the covariance matrix of x, A transpose. Let's apply that to that. And we've got our covariance matrix of parameter error. That is our propensity for parameter error, which I'm going to loosely equate to parameter uncertainty. It gets a bit better. Suppose that the covariance matrix of measurement noise is proportional to the identity matrix. That is, the noise associated with all measurements is independent of each other. I can actually find this proportionality constant as the minimized objective function divided by number of observations minus number of parameters. If I do that, this equation becomes a little bit easier. Things cross out and it becomes even nicer. So I've got now a covariance matrix for parameter error, loosely equated to my uncertainty, parameter uncertainty. So let's go a little bit further. Why am I building this model? I'm building this model to make a prediction. And here's my prediction. Prediction S, S for scalar, equals the sensitivity of, it's the sensitivity vector, the sensitivity of the prediction to each parameter times the parameter value. However, when I make a prediction, I make it with the calibrated model. So I get it wrong. How wrong? Propagation of covariance comes to our rescue yet again. Here's my potential for wrongness, my predictive error variance, easily derived through just substituting this into here. And remember from the last slide, we characterized CP minus P. So there is a beautiful little equation for my predictive error variance. So I've done it. I've calibrated a model. I've parsimoniized manually, obtained my parameters, quantified measurement noise, and I've got the uncertainty of my parameters and my prediction. I've arrived. Well, not quite. Manual regularization's got some deep problems. Firstly, it's manual. How can I be sure that that inverse exists? How can I be sure that I've parsimonized enough, that I've got enough parameters that'll extract information from the data? What if I parsimonize improperly and I create measurement noise with serious non-diagonal elements for that C epsilon, which I almost certainly will? These are problems, but there's even a bigger problem. So this is my term for predictive uncertainty. It depends on measurement noise. Where about are all those parameters that I've just obliterated trying to seek an inverse for this matrix? What if my prediction depends on parameters that I've wiped out? The parameters that I can't estimate are just as important as those that I can when it comes to assessing predictive uncertainty. So manual regularization gives us a few insights, but leaves us with many problems. So let's move on to singular value decomposition. Here's our situation statement. Let's focus on that Z matrix. Stated without proof, one of the most beautiful theorems in mathematics. Any matrix Z, whether it's long in this direction or that direction, can be decomposed into three very special matrices: U, S, and VT. Don't forget T is a transpose of another matrix, V. Transpose, you turn it on its side. U and V are square orthonormal matrices. Remember orthonormal from the previous webinar? Let's look at this a little more closely. An S has 0 elements off the diagonal. These are very special matrices. So U, orthonormal, that means its columns are unit vectors. Its columns are, each column is orthogonal to every other column. Collectively, these columns span model output space. This is a new coordinate system for model output space. VT, well, because this is transpose, we look at the rows. Little v1, little v2, row vectors. They're unit vectors, got a magnitude of unity. Each is perpendicular, orthogonal to each of the other ones. Collectively, these unit vectors span parameter space. So this is quite beautiful. And my singular values down this diagonal, they're all positive, start off high and get lower and lower. They either run out or they become 0 somewhere in here. So let's make use of that. So let's flip V on its side so that its unit vectors, which span parameter space, are vectors, they're columns. Now let me count the number of columns until singular values become 0 or run out. Let me count the same number of columns over here in the V matrix. Suddenly, a beautiful thing happens. I partitioned V into V1 and V2. V2 is the null space. V1 is the orthogonal complement of V2, which is the solution space. What have I just done? Well, something amazing. Now we know that any vector which lies in the null space has to be a linear combination of the vectors which are the columns of V2. And we know that Z multiplied by any of those vectors is 0. That means that the data cannot inform anything in the null space. That means when it comes to calibration, this is a no-go area. This is mathematical fantasy land. If I go into the null space, who's to know I'm going in the right direction? Because the data is not informing me. You want a minimum error variance solution to the inverse problem? Stay out of the null space. Singular value decomposition has given us the null space. So let's make use of these concepts. And for the moment, let's ignore measurement noise. So I'll subject Z to singular value decomposition and derive that third blue equation. Partition according to solution and null spaces, the next equation. Multiply out by construction. S2 is 0. So now I've got an equation which relates what I observe to things that only occur in the solution space. So if I'm going to back calculate any parameters and I want to stay out of the null space, I don't want this term. I've now got a term that I can work with that'll keep me out of fantasy land. So there's that equation. Pre-multiply both sides by UT. But look, orthogonality, things cancel out. Now I'm going to pre-multiply both sides by S1 negative 1, the inverse of S. Now this is another beautiful thing. By construction, S1 is a diagonal matrix and every term on that diagonal is positive. S1 negative 1 exists. Singular value decomposition puts me in a situation where I never have to take the inverse of a matrix that I can't take the inverse of. There's no guesswork here. It'll always work by construction. So the only time I take an inverse, I can take that inverse. Unconditional numerical stability is the result. So they cross out. And I then have an equation which is simplified, which I then pre-multiply by V1. Both sides of that equation I now pre-multiply by V1 to obtain this equation, which is actually my solution. Let me show you what I mean. But before I do that, let's recall from the previous webinar that V1, V1t is an orthogonal projection operator, in this case onto the solution space. So this is what I got. Here's K. Here's the parameters of the real world that I'll never know. Singular value decomposition tells me that the most I can ever know is the projection of reality onto a much smaller dimensional space. So here I'm characterizing parameter space with 3 dimensions. And here's my new coordinate system in parameter space. Little v1, little v2, these are the vectors spanning the solution space. Little v3, I'm going to assume spans the null space and it's only got 1 dimension. All I can estimate is the projection of reality onto a much smaller dimensional space. So what are the properties of this solution? It's unique. It's all I can get out of the data. I can't get any more than that. I can't wander into the null space. By staying out of the null space, I've obtained a solution which has no possibility of bias and hence is minimum norm solution to the inverse problem. It's also the same as the Moore-Penrose pseudo-inverse. Furthermore, the only inverse of a matrix that I have to take, it's unconditionally numerically stable. The solution is minimum norm because if I go above or below that solution space, this green vector gets longer. And minimum norm translates into minimum error variance if the prior covariance matrix of my parameters is proportional to the identity matrix. So near, yet so far. I've almost got the holy grail of model calibration, a minimum error variance solution to the inverse problem, but it depends on a condition that can't be met, because remember last time we said we acknowledge the fact that parameters show spatial correlation. My CK has off-diagonal elements. Therefore, it seems I've lost the possibility of getting a minimum error variance solution to the inverse problem. I got minimum norm, I got uniqueness, I got mathematical stability, but I haven't got minimum error variance. Well, it just so happens that all is not lost. Here's our prior covariance matrix. Remember, we bring this into the inversion process. This is something that comes out of site characterization, ideally. Let's do singular value decomposition on CK, USVT. But in this case, remember we said last time, CK is positive definite. Therefore, I can write that as EFET, where E features on both sides because of the symmetry. Now let me define this vector J, which is transformed from K, just using the two matrices that arise from singular value decomposition of CK. Now let me ask, what's the covariance matrix of J? Our old friend propagation of covariance comes into play again. So I just apply this equation to that equation. Now I recognize that CK is this because of singular value decomposition. Insert it. Orthogonality comes to our aid because the transpose of a square orthonormal matrix is its inverse. Things cross out everywhere, and the covariance matrix of J is I. Problem solved. This is called the Cahunan-Louvre transformation. So if I can estimate J instead of K, and then back calculate K from my estimated J, I've got it all. I've got uniqueness and minimum error variance. So let's go back here and let's assume now that I've done my Cahunan-Louvre transformation. So I do singular value. So there now is my solution to the inverse problem. And if I've done my Cahunan-Louvre transformation, this is now unique and minimum error variance. So now let's go a little bit further. SVD is giving us so many insights here about what calibration can and can't achieve. Can it give us some more? In particular, can it tell us about what's the best place to do the truncation here? Do I define my solution space just when the singular values run out or get to zero? Some of them are pretty low in here. Should I actually relegate them to values of zero and make my null space a little bit bigger so that I make my solution space a bit smaller? Why would I want to do that? Well, it turns out there's a real good reason for that, and it is yet another insight that singular value decomposition gives us into history matching in general and model calibration in particular. So here's my solution to the inverse problem obtained using singular value decomposition. Let's substitute this into here. Just multiplying out, that's what I get. Let's do singular value decomposition of Z. That's what I get. Partition into solution and null spaces, and now I can assign elements. So I can move between these null. I can assign elements of the solution space to the null space. If the singular values are too small, I can just make them zero. Hence, S1 becomes part of S1 becomes S2, which by construction is 0. So I end up with a simpler equation. UTU cancels out, the beauty of orthogonality, where the transpose of an orthonormal matrix is its inverse. S1 negative 1 S1 crosses out, and I have equation for my estimated K in terms of the real K, which I'll never know, and measurement noise, which I never know. Subtract that from my real parameters, I've got an equation for parameter error. Use a beautiful equation here, a matrix identity. Substitute into here, and I've got a nice simple equation for my parameter error. Now, as before, while I've got an equation for parameter error, I can't actually apply that equation because I don't know K and I don't know epsilon. But I can say something about my propensity for parameter error. That is about my uncertainty. And note that this time, unlike on the previous occasion, this term includes the cost of uniqueness, the stuff that I've had to simplify and leave out of the calibration process, but SVD has left it out for me by defining the null space. And that null space isn't just parameters, it's combinations of parameters, because those little v1, little v2 vectors, they're combinations of parameters. So singular value decomposition has done simplification for me, not in terms of parameters which I amalgamate and leave in and leave out, in terms of combinations of parameters that are solution space, null space. It's done it in an optimal manner because it gives me a predictive error variance for which the predictive error variance is minimized. And now I have an equation for my parameter error defined in terms of what I've had to leave out and what I can include. So this is really good. So let's just look at this equation and what it's telling us. It's saying that here's my parameter set K, partly in the null space, partly in the solution space. I'll never really know it. All I have a right to ask for is the projection of that parameter onto the solution space. I get that wrong because there's noise in the data. And my wrongness has two terms. That which results from noise in the data, that which results from the need to get a unique solution to the inverse problem. And this term here normally far outweighs this term. And the less data we got, the bigger this vector will be compared to this vector. And my equation for parameter error includes both of them. So this is a good situation. I'm now able to define parameter error, and it's able to include what it needs to include for this equation to have integrity. Now, I can't apply it because I don't know K and I don't know epsilon, but I can work out my propensity for parameter error. And to our rescue, once again, comes propagation of covariance. So if I apply this equation here to this blue equation, I get this top blue equation. Here's my covariance matrix of parameter error. At the heart of it is CK, my prior covariance matrix, and my statistical characterization of measurement noise. Now, suppose that I've done my Cahoon-Louvre thing. CK is proportional to the identity matrix. Suppose that C epsilon is proportional to the identity matrix too. That equation simplifies because we can put the identity matrix here and here. Orthogonality allows things to cross out. And that equation becomes simpler. Now let's use our model to make a prediction. The true prediction is S equals YTK. I make a prediction with calibrated parameters, which we now know are wrong, probably very wrong, but they're minimum error variance. Why? Once again, is the sensitivity of the prediction to the parameters. Here's my wrongness of the prediction I've got to make. I can't correct it, but I can look at my propensity for wrongness. That is my predictive uncertainty, roughly speaking. Propagation of variance to our rescue. Once again, apply this equation to this equation. Now we got CK minus K from the previous slide. And there is my equation for predictive error variance, including all the terms that it should, to ensure that I don't understate the error variance, that is the uncertainty of any prediction I make with that calibrated model. So let's now go back and answer that question we asked before. Where do I truncate? Here or here or here? This equation can tell me. So let's plot up the number of pre-truncation singular values and look at these terms. This first one goes monotonically down. The further I move that truncation point to the right, the more information I am trying to extract from my calibration data set. If I don't extract any information, 0 singular values, then that's the prior uncertainty of the prediction. It gets lower and lower and lower as I extract more information. Unfortunately, extraction of information comes at a cost. And that cost is this -2 superscript on the S1 vector, a matrix. As singular values get smaller and smaller and smaller, that term gets larger and larger and larger. So what that says, what singular value decomposition is telling us, yet another insight from SVD, that the more we try to get at those little skerricks of information that can provide the detail of hydraulic properties, the more that information is contaminated by measurement noise. It's there, but we can't get at it. So there's a minimum in that curve. This is where the predictive error variance is minimized with measurement error and whatever is responsible for model to measurement misfit taken into account. If I truncate to the left, there's information I could have got which I didn't. But if I go here, I've overfit. And we've all been told forever about the problem of overfitting. We've all been told that if you use too many parameters, you're going to overfit. Well, you don't have to overfit. You mustn't overfit. SVD tells you that you shouldn't overfit. And it also tells you how to not overfit. The lever that we can use to prevent overfitting is the number of pre-truncation singular values. So just because, and I still hear it said that too many parameters leads to overfitting, it explains looking at reality right in the face and using that equation which encapsulates all the complexity of a system allows us to get a minimum error variance solution to the inverse problem, and in the process we learn how not to overfit. And we also learn why overfitting is a problem. So SVD looks like, well, it's done everything for us. Unconditional, numerically stable, minimum error variance solution. The insights are amazing. We understand flow of information and overfitting. But there's not so good things. It all hinges on that Carhoonan-Louvre transformation. So we've got a CK, but we all know that covariance matrix is a pretty feeble description of a very complex hydrogeological reality. So basing everything on the ability to do a Carhoonan-Louvre transformation of a covariance matrix, that's very thin ice in terms of the integrity of this process. The other thing is that just knowing where that cutoff point is, the number of singular values, it's a lever, it's a good lever, but if it's an integer lever, it's not a continuous lever, and we don't know ahead of time just what is the right truncation point. So singular value decomposition is taking us so close to where we want to be, but not quite there. However, it has given us unconditional mathematical stability, numerical stability, and whenever in the equations that I'm about to show you, we have an inverse, we will use SVD to do that inverse, so we will lean heavily on its ability to conduct, excuse me, matrix inversion with unequivocal numerical stability. So now look at Tikhonov regularization. As I said earlier, this is normally our regularization workhorse. Tikhonov was a Russian mathematician, geophysicist, who did a lot of the maths which showed how we can attain uniqueness and minimum error variance using this kind of regularization. The beauty about Tikhonov is its flexibility. I'm going to show you one form of Tikhonov regularization, which is often called Bayesian inversion, but it's not the only form, and that's the beauty of it. We can, using Tikhonov regularization, tailor the inversion process so that it is ideally suited to the hydrogeological context in which we're working. So let's see how to do it. There's our situation statement. Now, if we do manual regularization or if we do SVD, we come up with a smaller number of parameters to estimate. If it's manual, we do the parsimmonization ourselves. If it's SVD, singular value decomposition defines combinations of parameters in the solution space which are uniquely estimable. Tikhonov regularization works the other way. It adds observations, and those observations are our expert knowledge. So we say before we go into this process, we know stuff. Our ignorance about site conditions is not complete because we've done site characterization. Let me assign every one of these parameters a preferred value equal to its expected value from an expert knowledge point of view. So what I'm saying is every one of these parameters now comes with an equation. So this matrix is now deeper than it is wide. There's a good chance that I can formulate a well-posed inverse problem. And every parameter is, if there's no information to the contrary, it's equal to its preferred value from an expert knowledge point of view. What's the noise associated with these observations? Well, the noise is the propensity of parameters not to be their preferred value, which is the prior CK covariance matrix. So for ease of what follows, we'll assume that the preferred value is 0. That doesn't remove any generality. It just makes the maths a bit easier. Parameters are departures from their preferred values. So here's the equation of my life as a groundwater modeler. They're the extra equations which encapsulate my expert knowledge through which I formulate Tikhonov regularization, stack them one on top of the other, and I have this equation. And this measurement noise term is actual measurement noise and the noise that accompanies my assertion that parameters are preferentially equal to their preferred values. So here's my situation. Now, this is very much like the situation that we've already dealt with when we are looking at manual regularization. I've got a matrix now which is deeper than it is wide. And here was the solution in that case. So in this case, however, X is Z stacked on top of I, and Q is this yellow matrix here. If I just substitute X and Q into the purple equation, I end up with this fairly ghastly looking green equation down the bottom. Now, it's not as ghastly as it looks. If I just do all the multiplications, I end up with a comparatively benign equation for estimated parameters. In practice, I put a little adjustment factor in front of this term. This becomes my tuning factor. This is the factor that I use to play fitting the data against fitting the prior conceptions. This is the lever that I use to prevent overfitting. I can always assign a value to that lever that prevents me from overfitting. If I'm using PEST, it calculates this value itself. You tell it the level that you don't want to fit better than, and it'll work out a beta squared such that you do not overfit. Now, this is a nicer lever than number of singular values because it's continuous and it can be back calculated from the fit that we don't want to get any better than. So this is a nicer way to prevent overfitting, but there's many nice things about ticking off. So we have that tuning parameter, and it can be shown that as measurement noise approaches zero, the solution that we get from this equation is exactly the same as the solution that we would have gotten if we had done Calhoun and Louvre transformation followed by SVD. So everything is converging. But it gets better than that. This is also the solution to an objective function minimization problem. And the definition of this objective function of which this is a solution, the minimization problem of which this is a solution, tells us a lot about what ticking off regularization is doing. We're saying fit the data. Here's the data misfit term. Measurement noise, observations minus model outputs. But we're saying fit that data in a special way. Fit that data in a way that minimizes departures of parameters from their preferred values. And if they have to depart, let them depart in ways that are geologically meaningful, with meaningful defined using my prior CK matrix. So this has got it all. It can be shown that the solution is unique. It's minimum error variance because, well, it coincides with SVD, and it's defined in a way that makes total hydrogeological sense, minimum departure from preferred values, from prior values, and departing in ways that make geological sense. Couple of problems still. I've got a big matrix to invert here, and the size of this matrix is the size of my K vector. If I got lots and lots of elements of K, I've got a pretty big matrix to invert here. Well, do you remember this? Do you remember this from the first webinar, this matrix identity? If we apply that matrix identity, the green equation to the yellow equation, we have another equation for our estimated K, and the matrix that we have to invert is just number of observations by number of observations. So I can choose the equation that's best for me, depending on the number of parameters and the number of observations. And I've still got my adjustment factor in there. And whenever we do a matrix inversion, we use SVD to guarantee numerical stability. But it gets even better. Remember back in the first webinar, I talked about conditioning. Remember I said that if we got two vectors, X and Y, and they've got statistical interrelatedness between the two. And remember I said that there are formulas available that said that if we get to know one of them, we can evaluate the conditional mean and covariance of the other. Well, here we've got exactly that situation. We've got K parameters, which are random, H, which are random because they're dependent on K. And then if we apply this formula here, and they're statistically dependent on each other because they're related through Z. So if we apply this formula here for the conditional mean of K, apply it to this equation, we end up with this equation. So everything is converging. This form of that Tikhonov regularization equation is exactly what we get from Bayesian principles, and that's why it's called Bayesian inversion. This is the conditional mean of K, conditioned by the observations that we make in the real world. And there's one more thing before we leave Tikhonov regularization, and that is its extreme flexibility. In practice, I don't have to use C negative K here. I can use an arbitrary matrix T, which encapsulates my hydrogeological conceptual model in whatever way I like. So I might say, I want to get more complicated than simply a covariance matrix. I might want heterogeneity to arise preferentially here because there's a fault here, but not here. I might want it to have directionality if it arises here, but not here. I might want smoothness or minimum curvature as a fallback position. If there's heterogeneity, I might want smooth transitions in some places, sharp transitions in others. Whatever my hydrogeological conceptual model is, theoretically, if I can encapsulate the way I want heterogeneity to arise in a matrix, be it linear or non-linear, that can form the kernel of the Tikhonov process, and the heterogeneity that will arise will reflect it. And that is the beauty of Tikhonov regularization. So let's finish off. Let's finish off with the resolution matrix. And if there's anything that presents a situation statement of what we can and cannot achieve through calibration, it's the resolution matrix. We sign up for calibration, we sign up for uniqueness. What's the cost of uniqueness? What is this parameter field that we get out of the calibrated model? And we know that, and we'll talk a lot more about it in the next webinar, that we really aren't serving the decision support imperative unless we quantify the uncertainties of predictions. But often the calibrated model is a nice step along the way. But if we do, but it's not the final step, but if we do search for and achieve the calibrated model, what have we got? Here's our situation statement once again. And if I've calibrated one way or another, I've found a Z negative, a generalized inverse of Z. Hopefully this approaches Z plus, something that's the unique Moore-Penrose minimum error variance inverse. And I've obtained a K underscore from H. Now, that could have been based on SVD, even manual. Whenever I calibrate a model, no matter how I do it, even if I don't use PEST or PEST++ or anything, I am seeking uniqueness. And what I'm about to say applies. There will be an explicit or implicit resolution matrix somewhere in the background, and it tells the stuff. So I've calculated K underscore from H. Let's substitute H into here. Now let's forget about measurement noise. K underscore equals Z negative ZK, and I'm calling Z negative Z the resolution matrix for reasons which will become apparent in a moment. So here's my resolution matrix. It's square. It's got the number of columns and rows that are equal to the number of parameters. Now, if Z has a null space, R has a null space, obviously, because it's product of Z negative Z. Therefore, it cannot be the identity matrix. In fact, the less data we have, the less R is likely to even be diagonally dominant. So it's going to have off-diagonal elements for sure. This has got big repercussions. So let's have a look at the element Ki of K, and that characterizes the hydraulic properties assigned to, say, this point in a model domain. Now remember what matrix multiplication does. We go along the row and down the column. So Ki is a linear combination of all the elements of the real K. We'll never know the real K. But what I see in the model is an averaging process of what appears in reality. The less data I've got, that more the averaging is non-diagonal, which means the less this point reflects this point, the more that what I see here is a smudged, smoothed version of reality, which I will never know. Same applies to any other point. And if we're estimating more than one kind of parameter, then these averaging weights that inhabit this row of R can cross parameter boundaries. Therefore, part of hydraulic conductivity may be recharge or storage. So resolution matrix makes it very clear that when I look at a calibrated model and I look at a certain place and say, is that the hydraulic properties at that place? The answer is no, no, no. What you're seeing is hydraulic properties of the same and other types, possibly integrated, smudged, averaged over a very large part of the model domain. Do not confuse this with reality. Nothing will give us reality. So a singular value decomposition, we know the resolution matrix, it's a projection operator. A little bit more complicated with Tikhonov, but can be calculated. There are utilities in the PEST suite that can calculate that resolution matrix for you. So with that, I've gone slightly over an hour. I apologize for the technical problems. And that's the story of model calibration. So with that, I'm going to stop sharing. I'm going to look at the question and answer box and see if there are any questions. But I seem to have lost question and answers open. No open questions. Does anyone want to ask a question? Okay, so I take it that that what I've said has answered all questions that would have been asked, and that if there's no questions, then here's a question, Justin. Thank you, Justin. Thank you for the compliment. How might you use the R matrix? Well, actually, in real life, I've never used it. Now, having said that, one of my students is actually using it because we're doing some really interesting work where how can we infer, is it possible to say something, can we back calculate the CK matrix from the calibrated parameter field? Now, you know, like it follows straight away that you look at the calibrated parameter field, you can't say, this is the heterogeneity that applies in the real world. No, because that's filtered through the resolution matrix. We may be able to say something probabilistic about real world heterogeneity from the calibrated parameter field, but it's only going to be probabilistic, and we've got to take account of the filtering action of the resolution matrix. So that's how we're looking, that's how we're using the resolution matrix. In general, however, there's no real use that we can put it. It's just and again, it's a lovely little sort of position statement of what we can and can't achieve through calibration. Okay, Lewis asks, how beta parameters defined to reduce overfitting? Well, internally to PEST, so you can do that. You know, you could do that manually. You could also adjust it in steps. You know, you could, if you run PEST in Pareto mode, and I think PEST++ has got similar functionality, you can gradually apply that beta and just look at the interplay between fitting the data and fitting prior conceptions. Within PEST, it just uses a bit of linear algebra and it says, okay, you tell it through the target measurement objective function, this is the fit that I want to get, and then it back calculates the beta and it revises that calculation during every iteration as the sensitivities are updated. So there's a few ways you can do it. In PEST, it's done automatically. Jeremy says, can you account for the effective parameters that were inappropriately left out of calibration? Well, not. You probably know the answer. I'm scared of answering this wrong. If they're left out of the analysis, you've kind of lost them. Now there are other ways that we can do uncertainty analysis. You know, there are ways that are, you know, if they're in there, you can use them to do, as we'll talk about next time when we talk about uncertainty analysis methods. They're going to wiggle when we look at the uncertainty of predictions. But if they're left out, you mean they're left out, you've lost them. Now, there are methods such as data space inversion, which are kind of slightly different, but they're still wiggling. They still have the ability to be stochastic. But I think, you know, the bottom line is if you've thrown them away, you've thrown them away. And that's pretty much it. There may be some heuristic things you can do to expand the uncertainty on account of it, but it's always going to be guesswork, I think. Okay, Chris, on the topic of overfitting, do you need to worry about overfitting for industry scale real world modeling projects? For example, in my experience, I've rarely seen models with an SRMS of less than 1%. Some of these models have 10,000 pilot points. Now, there's two different issues here. Firstly, the SRMS, I don't think that means much. You know, the S in front means scaled. That doesn't mean much to me. You know, that means that if you've got a model domain with a lot of topography, you get a nice big scaling factor, so your SRMS can look a lot better. Doesn't mean much. Now, the overfitting has got, you know, it's got to do with the fit, but it's also got to do with the noise. So the RMS just tells you the fit, but you got to know the noise. So if you got a lot of noise, you know, anything can be overfitting if you got enough noise. So it all depends on the noise. Now that begs the question what the noise is. Now we know it's more than model to measurement noise. We know that it's really misfit comes from defects in the model. Now, when we're doing regularized inversion, when we got lots of parameters, we kind of know that we've overfit, because if you look at your parameter field, and if it's a minimum error variance parameter field, and it's got all these yucky bumps and lumps all through it, and you say to yourself, that's ghastly. I think some of these bumps and lumps are rising from overfitting. That's really how you tell. You know, it does indeed become a little bit subjective. So you say, are those bumps and lumps telling me something about heterogeneity that I didn't know existed? Or have they got this character about them where they just look spurious? And this is where it starts to get really subjective. So, okay, I've overfit if I've got too many bumps and lumps in that parameter field. I don't believe them. I can get rid of them just by reducing my fit. And often you don't have to reduce your fit much to get rid of a lot of those bumps and lumps. Okay, that's satisfying. But in the meantime, you're saying, okay, those bumps and lumps arise from conceptual inadequacies. Is there something that the calibration process is trying to tell me here? There's no answer to that question. It depends on the prediction you're making. If those bumps and lumps are arising in critical places that are critical to your prediction, perhaps, you know, on the one hand, you could say, overfitting, go away. Or on the other hand, you could say, there's stuff going on here that may be important to the prediction. I need to revise my conceptual model. So there's no, like, you know, this is how so many questions are answered in the last webinar. So there's no answer to these questions. And that's the unsatisfying thing about modeling. There is no answer, but if we know the principles, we can supply the necessary subjective answer ourselves. Satisfying? No, but it does mean we got to know what we're doing, and that's pretty important. Anonymous, I take it the R matrix incorporates the effect of parameter compensation. Can the simple complex framework be used to identify strong parameter compensation and reconceptualize the hydro model? Yeah, you're right. So if you've got parameter compensation, compensation for what? Parameters that you've left out, parameters, parts of the model that you've fixed. Now, when you're fixing parts of the model, they may be parameters or they may be the model structure. You can say, well, I'm actually doing regularization here. I'm fixing parameters, can be using the word parameter in a very broad sense, because, if you don't know model structure exactly, then it's effectively a parameter, except you can't wiggle it. And that says a lot about how complex your model may need to be, because if you've got stuff that's embedded in the structure and you can't wiggle it, then you are maybe manufacturing bias. But anyway, that's another story. Yes, it's not in your R matrix, so that's the problem. So if you've got a simplistic structure and you've got obvious compensatory behavior of the parameters, it's in the regularized, the resolution matrix that you would have built if the structure could be a parameter, but you can't build because the structure can't be a parameter. So yet another unsatisfying situation. Do you make the structure simple, but that has its own bias-inducing possibilities? But if your parameters can then be more abstract, but at least they can wiggle more, so you're playing parameters that can wiggle but are more abstract against structure that can't wiggle but can induce bias. Which is the best way to go? Again, no answer. It's going to be context specific. Know what you're doing it and answer it the best you can. Any other questions? Okay. Well, listen, everybody, thanks very much for putting up with me with the technical problems. We've gone well over an hour. I hope you've enjoyed this. This webinar, of course, will be available for download from the GMDSI website shortly. And in 2 weeks, we will take the next step of our 3-step journey, and we'll look at parameter and predictive uncertainty. So thank you once again, everyone, and thanks for Fiona for being in the background and making sure this all works. Thanks very much.